Welcome everybody. We welcome you to the NOAA webinar series. Our webinar today will be about the capabilities of the discrete dipole approximation for simulating optical properties of atmospheric aerosols. The presenter is Maxim Yurkin, who has received his bachelor's and master's degrees in physics from the Novosibirsk State University with honors, and dual PhD in computational science and biophysics from the University of Amsterdam and the Vodotsky Institute of Chemical Kinetics and Combustion in Novosibirsk. Currently, he is a senior researcher at Özyeğin University in Istanbul, and his research interests include the theory and simulations of electromagnetic scattering, the discrete dipole approximation, and inverse light scattering problems. Specifically, he has made multiple important contributions to the theory and numerical efficiency of the discrete dipole approximation, and he is the main developer of the open source ADA code. So, Maxim, hello, welcome. We are very happy you are here. This is a very interesting topic for us. We will have your presentation for about 40 minutes, and then at the end we will have a discussion. Everybody, please use the Slido to post your questions or the chat. So, Maxim, please go ahead.
Yeah, thanks for invitation to this webinar. So it's a nice opportunity, and one moment. Yeah, so, well, here's a basic plan of what I will be talking. So a little bit about light scatter and discrete dipole approximation, then about the other code, and I will show some application examples specifically for atmospheric aerosols. I think you all know everything about light scattering. So what is it? That it's used for kind of dispersed media everywhere in the world, basically. And also, it's usually, we can say a lot of nice things, how we can do remote sensing, solving inverse problems, etc. But the first step is always to solve the direct light scattering problem. So when we have some particle and we want to simulate light scattering or interaction of electromagnetic radiation with it in any spectrum, whatever. I won't cover all existing methods, definitely, but the most general methods, I think, are volume discretization ones, because they can easily incorporate any inhomogeneous particles, and that's probably, well, the most interesting particle that exists, well, anywhere, including aerosols. And even among these volume discretization methods, there is a lot to choose from. Here is a small classification on this slide, but if we go to volume integral equation in frequency domain, which is like one of the options. So again, I won't really talk about like which method is better, etc. That's a very, well, a separate topic. I will mention like maybe 1-2 slides at the end about it. But overall, well, volume integral equations are widely used, and methods based on them. They have many different words, naming, and discrete dipole approximation is one of them. Like the difference between them, or where the boundary between them comes, is really, again, a vague question. But, well, anyway, so that's where discrete DDA lies in which field, and let's talk about it in more detail. So, well, the most simple, like, physical picture, it spans from the point dipole. So if we have a point dipole, which is time harmonic, then we know the field which is produced by it anywhere in space. So dipole is here, anywhere in space, you have this formula, and G as well, it's a bit long equation, but it's still trivial one, so no special functions, whatever. And then if we take a set of a lot of such dipoles, we can just consider how they interact with each other and with the incident field, and get some system of equations. So that's kind of the naive or physical picture of the DDA, that we have any, well, so generally solid particle, potentially inhomogeneous. We just replace it by a set of point dipoles, which is kind of intuitively obvious that you can do it if the dipoles are small enough, and then, well, you just have the system of equations, solve them. That was the original, derivation of this method already, like, well, yeah, it's 50 years ago exactly. when it started, and then Drain with coworkers popularized this method a lot, and it was always like advertised like a very simple method, like you can, I don't know, explain it with your hands, very simple. I think that is good, but I also like to add that it can be also derived as a rigorous corollary of Maxwell equation. So that's not just some method which we don't understand how. It's actually based on volume integral equations, as I mentioned previously. Well, I don't want to discuss all these formulas, but important that you start with some equations which follow from Maxwell equations, so just one of the standard ways to rewrite them. Then we do volume discretization, and then we arrive at this. So that's kind of the master equation. Here, the red alpha, it's polarizability of dipoles. So here we can already, because it's volume discretization, we can call them voxels. So that's shown here how we can divide any particle into voxels. And then this will, the only part which depends on the like local effective index. So, well, here are some formulas. So basically it's determined by the local permittivity or effective index. And two other are here, it's J and M are the interaction term, which we call, and self-interaction term between the dipoles. So I just mentioned them here that they can have slightly different expression determined by the formulation of the DDA. So like we can have various formulations and it will affect only these two terms that are here, but it will anyway will be some functions which can be computed. So again, we have this master equation. Solving it's the main computational bottleneck. And once we do it, we can determine anything we want. So it can be like internal, near, or far fields. For atmospheric applications, we are mostly interested in far fields. We can compute any, I don't know, cross sections, a symmetry parameter, whatever you want, like LiDAR ratios, backscattering. And the main conclusion of this part is that DDA is numerically exact method. Numerically exact is, I mean by this that if you take like infinite computational resources, which, well, surely not available, but we can dream of it. So if we take, then we can get as good accuracy as we want for a given problem. So that makes it different from, say, I don't know, geometrical optics method, where you make some approximation in the beginning that you solve not the Maxwell equation, but something else. And then you have some error which you can't get rid of with just computation. So for DDA, it's not the case. So in principle, at least for not very large problems, we can hope to get good accuracy and we can hope to control this accuracy. Also, let me just briefly mention that you can use not only plane waves as incident field, but more intricate ones like point dipoles placed near the particle, inside particles, even the field of the electrons. You surely don't need it all for atmospheric applications, but if you come up at some point in your career or research at some of these problems, that just know that DDA can also be used for these problems as well. But we will talk only about plane waves here. As I mentioned, the main bottleneck is solution of the huge system, I can say, of linear equations. And well, if you just look at what is written here, that you have this 3n linear equation, n is the number of voxels or dipoles, which can be up to, well, 1 billion, at least that's what I've tried, well, myself, and I don't know if anybody tried larger, but well, that's the order that is already can be done, but matrix of the system is dense. So if you combine this, it seems it's completely undoable, because like even if you use some method which is order of n squared, or standard matrix inversion will be order of n cubed, that's completely undoable. Well, the good thing here is that we have a regular rectangular grid, well, almost always in the DDA. So it's like maybe not necessarily used with the DDA, but all the practical application, they will use this regular grid. And then the matrix that we get, it's dense, but it's tuplets, more specifically multi-level block tuplets, which means that it has some numbers the same over diagonals as shown here. So that's one level, simple tuplets matrix. We have a bit more complicated, but the important thing that because of the special structure of the matrix, we can turn the memory requirements down to order of n, and matrix vector product, so multiplication of this matrix with any vector, can be done also almost linear in N using FFT. And that means that if we combine this with iterative solvers, which usually converge in number of iterations much smaller than the number of dipoles, so, well, not always, but in most cases, then we get overall computational complexity, which is linear in N. And that's the main reason that makes such huge N possible, as written here. So DDA in this sense is, it's kind of very simple method, you can call it, but it's also very efficient, at least for some kind of problems. But that's a blessing, yeah, but it comes with some curse. And the curse that actually it becomes like a very efficient hammer, which you can't improve in many sense, because if you think of some ways to improve it, as shown here, like some, I don't know, some adaptive grids or whatever, which is, well, used a lot in other methods, then here it will first break this FFT acceleration. And once you get from order of N to order of, I don't know, N squared even, then immediately it becomes very slow. So you don't want to do it. And because of that, DDA kind of stays simple. So many improvements can't really be used for it. So it's, well, both maybe good for users that it's simple, but not that good in terms that, well, further optimizations are not necessarily possible. Okay, a few words about DDA formulation. So that's a picture from my old review on the DDA. It has not changed a lot since then. I won't surely describe all of that. I just want to mention that there are a few formulations that modify the interaction part and many formulations that modify polarizability part, or this M term, which I mentioned previously. Actually, these don't have a very significant effect on, say, computational performance. And these sometimes have. So these two formulations, so that's abbreviations for filtered coupled dipoles and integration of green standard. So these can be important, can improve performance significantly in some cases, but the drawback is that we no more have, well, exactly point dipoles, but more like finite voxels. So as I showed you picture before, that you have like cubical or even cuboid voxels, and then you well, consider some integrals over this voxel. So this all can be computed. You don't need to worry about it if you use the code or whatever, but just the simple physical picture of point dipoles is not, well, exactly applicable, I would say. I mean, the equations are the same, so they don't change that much, but these kind of terms in this equation become more intricate. Okay, so let's go to the codes that exist. So actually there are a lot of codes, but most widely used, and I don't know, maybe, well, 90% or more of all papers on the DDA use either ddisket or ADDA now. So there is two codes. ddisket is all the codes, and actually I should say that I think ddisket is one of the like first truly open source codes in the light scattering community. So it actually like set the standard for also for ADDA and for many other codes for other methods that basically, well, because I speak with people in other communities, well, I think nowadays it's more or less a standard that to use open source code, but I don't know, maybe 10 years ago, it was not yet that. But in light scattering community already in 90s, like everybody who was doing a new code, they would, well, most probably release it as open source. And that's also partly due to ddisket. So I don't want to compare like in a lot of detail these two codes. For many problems, you can use either one or another. And even like you can use shape files prepared for one code and just go to another code and run it. The only thing about ADDA, well, so as I already mentioned, I'm like one of, well, if you can call it the lead developer of this ADDA code. So I would naturally advertise it. Here is some history about it. Well, I think history is not that interesting, but just now that it's open source international project, so we have around 10 developers now, well, kind of contributors at least, so who at some point contributed the code to ADDA. So it's on GitHub, well, as you would expect. Well, we are kind of slow of releasing a new version, but it should be available soon, but since it's on GitHub, actually you can just go and download the current code from the master branch, and it has some new features. But for atmospheric applications, I think you just can stick to the stable version 1.4, and it will have, I think, well, all the features that you need. Yeah, so that's about ADA. And if we compare ADA to DDSCAD, so for just in case somebody is using like DDSCAD code and you are considering whether you should switch to ADA, I think the most important reason why you want to do it is if you are not satisfied with performance. So you want to do some large particles and they don't fit into the memory of a single computer. And that's where ADA comes with this unique feature that it has MPI-based. So MPI-based means that you can distribute it over the cluster with distributed memory. So not just like one workstation which has own memory inside, or well, on some supercomputers, you have also these huge nodes. But usually you have a cluster which on each node, computational node, you have, well, a lot of memory, but not so much memory. And to combine it for a single huge simulation, you would want to, for the code to be able to use MPI. So that's the thing, and ADA can use it. So for these huge simulations, you can do it. Also, we have GPU acceleration, but I should say that it's not that efficient because the main part is FFT, and FFT is actually not that well parallelized for GPUs. So that's just the kind of problem we have with the algorithm are not that kind of suitable for GPU acceleration. But you can get, I don't know, with modern GPU cards, maybe up to 10 times acceleration or several times at least you can hope for. Okay, so just as a single example of what can be done, one of the recent papers we managed to do up to 1 million spheres simulated with ADA, so on a large supercomputer. So if you want random orientations, it was 100,000, but in fixed orientation, we do a few tests with 1 million of spheres, each is, well, smaller than the wavelengths. It's not really relevant, I think, for atmospheric application, not immediate like that, but shows like the total capability. Well, a few like advertisements that I claim it to be reliable. So the code is used in many publications. I think I've gathered about 30 countries. It's also in some top institution, including National Observatory of Athens. And so it's also, we tested it in comparison with other codes and other methods, but again, it's not that easy to compare different methods, but at least for like simulation results, so if you're not talking about performance, but just that they produce the same result, this can be done. So we actually compiled a list of different comparisons, so you can take a look. And I think the most important part for reliability is this open development process. You not only release codes like once in a few years, but actually the whole development is like open for the community. So at any point, anybody can download the codes, test, find some bugs, etc. So that's ongoing. That means that the stable releases are, well, really stable. It's also easy to use. Well, a lot of information here, but I think the most important that you can just download it and compile. If it's Linux or Mac, you just compile it with a few commands, well, like make as usual. And for Windows, you just download and run it. So that's possible. Also, we have a graphical user interface. It's kind of in beta version still. So actually, Dmitris Munyov is my collaborator, is developing in it on his own. So it looks like this. It's maybe I won't recommend it for like large scale production runs, but if you're never used ADA and want to give it a try, I think that's the most simple way for a quick start. And then after, basically you can choose anything with your mouse here, and then it will give you the command line, which you can then use for some scripted execution to have some parameter sweeps or whatever. well, we go to applications. As I mentioned, DDA is just a method to simulate electromagnetic interaction, so it can be used almost anywhere. But, well, we are interested in meteorology or atmospheric applications, so that's aerosols, hydrometeors. And, well, finally, here are some few examples. So surely I selected like the most complicated particles. You can also do some simple, like, I don't know, like hexagonal ice columns. So that's also have been done a lot, but that's, I think, more or less the most complicated stuff that I have seen. So yeah, over the last 2 days, I have actually scanned through the papers to take out all the nice examples. So, well, I won't show you like the simulation results because another problem with all this data that I was not involved in any of it. So most of it was computed with ADA, and even if it was computed with DDSCAT or other DDA code, that means that you can easily reproduce it with ADA. The reverse is not necessarily true if it's very huge particle, as I mentioned before. But yeah, so, well, people use DDA and ADA for such shapes. So, well, I think it's all written here. So, you know, probably better than me what's the difference between Gopal, snowflakes, etc. So I won't bother with you. But basically, anything that you can model or, I don't know, draw, whatever in your computer, you can put into the DDA and simulate it. So that's possible. So even some, well, last interesting stuff is basically surface roughness on top of the ice, where they said that, okay, we have like huge ice crystals for example, for visible wavelengths, which means that we will use geometrical optics, but then we have some surface roughness on this. So we will use DDA to simulate this surface roughness and then hybridize the results with geometrical optics somehow. So this kind of stuff is also possible to do. And then for this surface roughness, it's not just like in free space, it's actually on the surface of the semi-infinite ice block. So that means that one of the features of ADA, which is usually not needed, is that it can simulate particles on top of substrate also quite efficiently. So usually you have isolated particles in atmospheric applications, but if you want like surface roughness on top of a large particle, then again, some options for efficient simulations are available here. Okay, so then also another is soot aggregate. So I was, well, once involved with Chinese colleagues in one of such work, but there are much more which are shown here. So again, surely you can do just simple fractal aggregate of spheres. So that's the basic stuff, but these examples show what you can do more. So you can do necking and overlapping between these spheres. Then you can change spheres to spheroids. I don't know whether it's relevant in practice, but seems nice that you can do it and try it. All kinds of organic, inorganic coating. Again, if you look at these papers, DDA simulations is actually like very basic stuff in them. So it's just like a tool. The most interesting stuff is how you model this coating. So that's like this shape, physically based shape models. So that's like the most interesting stuff. And well, mineral dust, again, I probably don't know all the examples that can be, but for example, recent paper of this year of marine aerosols, well, actually, Michael Canet and his PhD student, they made a lot of papers during several years, but that's like the last of them. For cubic salt crystals, where they are supposed to be cubic, but not really cubic even to start with, and then they got covered with moisture, and then the corners got dissolved. So then you have this shape as shown here. So again, this can be simulated. Then for some Gaussian random spheres or spheroids are widely used as a simple, well, analytical model that you can easily kind of generate in your computer, and that's examples how they used. And then also, if you're thinking about some irregular inhomogeneous shapes, that was also used. So I think here it's not really visible here, but it was something like Gaussian random spheroid, but then with some surface roughness algorithm that basically bites parts of the particle from it. So it results like this. And also, if you look actually in many shapes, you see that they are already visualized already with these cubical voxels. So that kind of shows why DDA is so convenient for such problems, because if you have some complicated algorithm to generate shapes, in many cases it will also operate based on voxels. So any physics that you have inside, and then you can directly transfer it to the light scattering simulation. So you don't need to do some, I don't know, surface smoothing or whatever that you would probably need for some other method. So also I showed like some examples. In some of these papers, it was really like only several simulations just to show, because they spent a lot of efforts to producing these models. In some, it was more systematic studies. But here, a few examples where really a huge databases were built for ice crystals, for mineral dust, which cover a lot of wavelengths, a lot of different shape habits. So from simple, like, I don't know, hexagonal columns to complicated aggregates, and some, well, for ice, I think there were some aggregates like that, like shown here. I'm not claiming that like DDA is the only method that was used there, because for large particles, you would inevitably go to something like geometrical or physical optics methods. There are also some volume discretization, time domain methods, for example, that can be sometimes more efficient, sometimes less efficient than DDA. So usually these papers, they combine several methods, but DDA is at least one of them. So that's also used. That again shows kind of the maturity of the method, that it can be used in production large scale parameter sweeps. And that's just, well, another recent example. Again, unfortunately, I was not involved in this science paper, but it showed that with DDA, you can get some details of the internal field. So here they studied how it affects aerosol photochemistry, basically some photo reduction of iron 3 in some aerosol particles. So actually the model is very simple, but you can also consider even some non-linearities. For example, the imaginary part of the effective index, so the absorption rate, it may depend on the intensity of the internal field. So this again can be easily incorporated into the DDA simulation. So again, it's becoming more complicated how you actually define your scattering problem. So most attention will go into it, but at least that shows that that kind of information is available from the DDA simulation, and you can basically get internal fields, then from internal fields get some feedback on your local effective index in each position and iterate it if needed. So that's one of the ways to solve nonlinear problems with the DDA. So yeah, I showed the examples. Let me talk a little bit about accuracy, because, well, surely that's a very wide topic, especially if you're like new to DDA. So you just take the code, want to simulate something, and then you open the manual, and it will say to you something like, okay, that's basically your responsibility to tune the parameters. So that's probably not what you expect to see, and well, it's not exactly the same, because if you run other code with just giving shape, size, etc. of the particle, it will produce some results. But so it has some built-in intrinsics for choosing the basically dipole size, how to discretize the particle, but the accuracy is not guaranteed. So for quick runs, okay, that's fine. But if you do something, well, more systematic, that I definitely recommend not to use it as a black box, even although the codes actually allow you to not worry about it. I mean, they don't ask you, don't insist for you to think about it. So yeah, there is a number of ways how you control this accuracy. Probably I will just refer you to the manual, which describes it. But one thing is to use different formulations of the DDA. So even if you have some fixed problem, try to play with the formulations, because any code can allow you to choose between a few at least, and then you can also change you can refine discretization. And if you refine discretization, one thing that I also want to show is Richardson type extrapolation. I don't know if you've heard about it before, but if not, that's that's a pity, because that's really a very beautiful thing which can be applied for many methods, not only DDA. And the idea is very simple. You have a method which depends, well, like here, on a single parameter. So that's basically the dipole size. Once everything is fixed, or you decrease dipole size, which means you increase the number of dipoles, and then you just compute your values. So you can do it several times. Here it's a lot of points, but you can compute maybe 5 points and then put a line or a quadratic function through it to the 0. And 0 means more or less this infinite discretization, which means infinite computer resources. So it's not reachable in practice, but you can extrapolate to it. And by this, you can both improve accuracy by order of magnitude in some cases, and also estimate the accuracy. So again, well, some details were shown already in this paper long ago, but again, if you go to other manual, for example, there are some description of it. So yeah, that's there are some ways to control the accuracy. So that's the main point here. Again, a few slides about, okay, when should you use DDA or some other method? That's very hard to say, because if you want to compare like two methods and say which one is faster, you should take care that they produce comparable accuracy. Because for any method, well, almost any method, you can sacrifice accuracy and make it faster, or you can get more accuracy, but at the cost of computer time. So if you want to compare which method is faster, you should somehow manage so that give comparable accuracy. Still, some comparison were done. So one example is shown here. That's very simple spheres, homogeneous spheres, non-absorbing ones. And you see that here, when relative refractive index, well, for air, it's the same as absolute. So when it's small and particles are not very large, so DDA is more efficient, and here time domain methods more efficient. Then if you add absorption, actually you can, well, quite large absorption, which happens, for example, for water, I think, and well, for ice also in some wavelengths. Then you can get, well, the method become comparable. So for example, somewhere here, DDA becomes again not that bad as for non-absorbing particles. So again, if you have absorbing particles, then it's kind of additional argument to use DDA over other methods. So it can solve the convergence problems which happens for large particle. Convergence, I mean the convergence of the iterative solver. And that's where I want to like get some future outlook. So because any method, as I mentioned, well, at least any rigorous full wave method, it will break down at some huge particle. So you can't increase the particle size without any limits. At some point it will break. So for DDA, first, just the computational time increases more or less as a third power of the size, just because the number of voxels increase with this power. But at some point, the iterative solver becomes slower and slower. At some point, it basically becomes slower exponentially, so it just fails to converge. So for example, some time ago, a few years ago, the limit was as shown here. And that's one of the ways to push this limit a little bit. So, well, you see for some refractive index, we pushed it a lot, but for some it's only, I don't know, 10, 20%, something like that. And that's how it goes. Yeah, you can't really, I mean, doubling the available size, it's really a huge endeavor. So I don't expect that it will happen soon. So I think the details are not the details, but just that you can play with the initial guess for the iterative solver. And that's already something, for example, with Arda, you can already do it. And that's Konstantin Injvatkin, my PhD student, was doing. Another idea which actually, again, appeared recently is circulant preconditioners. So in the beginning, I mentioned that preconditioners, standard preconditioners are not working for the DDA because they break this FFT acceleration. But there are a special class of them called circulant preconditioners, which can be compatible with FFT. But still, because the matrix is multi-level block toplets, so it's a bit complicated, this internal structure, the preconditioner, it does break some FFT acceleration. So it helps a lot. Sorry. it helps a lot with when iterative solver starts to break down, this preconditioner can solve the problem, but it also kind of have drawbacks, and that's why it's efficient usually not for standard like compact particles which have similar dimensions along each axis, but for something like shown here. So it's like very oblate or very prolate particles with aspect ratio like 5 or more. Then you can expect that it works. And also, well, particles inside a multi-layered substrate, for example, but that's not relevant for atmospheric applications. So again, you can't really use it in some available codes. That's kind of a problem. Actually, there is a code by Patrick Chaumet, if DDA it's called. It's like Institute Fresnel DDA or Idiot Friendly DDA. There are two like explanations to this code. But I'm not sure if this precondition is implemented in this code. So it's by the same author. So you see here the paper, but again, I have not tried it in this code, but that's one of the options for large particles. And another idea, well, I just want to show that like progress is ongoing in this direction, that if, for example, you have multiple effective indices, then it turns out that we have multiple linear systems to solve, and then they can be written so that these systems differ only by this term here, which is called shift. So it depends on the effective index of each particle. So usually if you want to build a database and you sweep over effective indices, the idea is that there exist special iterative methods which are called shifted conjugate gradient methods, and we already working with one of it, so it's not yet implemented in Ada, but already we have some test results on some separate code, which shows that basically you can run from 10 to I don't know 100 effective index simultaneously, and at the cost, computational cost comparable to a single DDA run for like the largest of these effective indices. So acceleration can be an order of magnitude easily in this respect for such parameter sweep application. So, well, it should be available here sometime, but not yet. But you can go there and track the progress. Again, Konstantin is doing most of it. Okay, so we arrive at conclusion, I think here more or less in time. So what I hoped I showed to you is that DDA is conceptually simple, general, and powerful method. Mature open source codes exist. So I will advertise my code, but DDSCAT is also good. Some other more specialized codes also are fine. So yeah, just choose whatever suits you and use it. It can be used for a wide variety of physical problems. But, well, again, for atmospheric probably not that relevant. We usually have quite classical one here. And although it can be used for any particle shape, so even for spheres, yeah, but why would you use DDA for spheres? You have the Mie theory, which works perfectly. So it's especially convenient for some really complicated, like irregular and homogeneous particles. When you do simulations, you should exercise caution with extreme effective indices. And also when the particles are large, both large and non-absorbing high contrast dielectric particles. So that's kind of a problematic domain for the DDA. I mean, you will see it. So it's not that it will produce some results and they will be, bullshit. So not like this. It will be more that it will just stagnate and produce some error that iterative solver does not converge. So this can happen for large particles. So please pay attention to accuracy and keep track of the development. So it's still actually, I think even since I think COVID started, there was some boost because it's maybe like for a lot of theoretical and computational work, there was a boost from pandemic times. Actually, a few new avenues of development, well, if not appeared, but at least accelerated. So it's all growing, and well, hopefully it will be even more and more efficient. If I want just to name one development which I'm eager to see is some hybridization of, I don't know, geometrical optics with the DDA or something like that. So basically, we do need a method which you can use for particles of arbitrary size, but with which you can actually control the accuracy. So with geometrical opticals, you just compute it once and then you hope that the accuracy will be fine. You can have some benchmark and say that, okay, for particles larger than, I don't know, size parameter 100, we expect that it should be fine. But it would be nice if you can have some series or whatever, or some iteration that you can put on top of that to improve the accuracy if you need it. And well, surely DDA is not like any unique method. It can be done with any other full wave method. But yeah, that's one thing that I think will be a great advantage for atmospheric applications. And yeah, if coming back to ADA, so here's some motivation here to use and provide feedback. So one thing I want to say, that there is a discussion group also. If you have any questions, well, I hope we will have a lot of discussion now, but then anytime, just write a question there, especially if you want to push the code to the limit. So, or if you are shy to write to a discussion group, just send email to me personally. No problem. So as I mentioned, I was not involved in any of these crazy particles simulations, but at least I know a lot of papers. So I thought a lot about how to do it efficiently. So if you have some challenging problem for the DD and don't know whether DD is suitable, whether it can do it, how to push most of the code, things like that. So please do not hesitate to contact me or the discussion group. Okay, so that's acknowledgement. Surely that was a lot of people involved who helped, contributors so far. Well, Alfons Huxer, who introduced me to the DD long ago when I was doing my PhD in Amsterdam, and many others. So thanks. And finally, so I'm now, since I left Novosibirsk, I'm searching for some position, professor, group leader. So if you know of any options, please let me know. Okay, thank you.
Thank you, Maxim. Thank you. Very nice presentation. We have a question in Slido. The people who want to ask something, they can also raise their hand if they don't want to write in chat or in Slido. So the first question is, we experience an evolution on GPU parallel computing, and this could be an opportunity for ADDA runs. Any plans for getting ADDA ready for such HPCs? So you mean several GPUs, and that's I think not possible, and actually no immediate plans to do it. So well, it basically takes some PhD student, probably from computer science, who will implement the code. So in principle, it's possible, and that's definitely a good idea to have. So for now, as I mentioned, for MPI, so if you have just a cluster of computers on each, you have one or several CPUs, each with several cores. So then you can use MPI to run on it. On GPU, right now, there is a code, well, like one of the, so you basically compile ADA in a special mode, and then it can run on a single GPU. And the main problem is the available memory. So again, it becomes like, I don't know, DDSCAT on standard machine, that basically you have so much memory on your GPU. It can be now, I don't know how many gigabytes, but still, if you want more, you can't do it. And to go from one GPU to many GPUs, well, that's not a trivial task for programming. So that's, I can't kind of say any, can't say that it will be ready this year. And probably I'm also, well, I should admit that I'm a bit not working on computational part this much. I mean, not really on computer science. So I prefer to do some, I don't know, like new formulation of the DDA, so that it will be like you can produce results with less number of dipoles into that, because optimizing. So some time ago, when I was a computer science PhD, I was really fond of testing like different processors, things like that. But then I got tired from it. So we need another guy who will be fond of all this stuff, and then he can do it. But that's a good thing of, I mean, open source projects. So if there is somebody and you can write a proposal for it, get PhD student, and then we can collaborate on doing it. Okay, so it is possible though, but there is no people assigned on doing this.
Yes. I mean, I don't see any principal differences. But another thing that you should understand, as I also mentioned, that you should not expect, I don't know, like 1,000-time acceleration. For example, if you read about GPUs now, then they say, okay, for some problems, I don't know, this machine learning or I don't know, code breaking, you take GPU and you're immediately 1,000 times faster. So that won't happen for the DDA because it's FFT. So FFT, basically, you can accelerate it, but it requires, well, you can call it global memory access. So it's you have this parallel threads, and they should exchange memory often between each other. So that's the bottleneck for the GPU simulation. So you can expect, like, I don't know, 10 times acceleration, and especially if you have access to such computer, then, well, you can use it for other, I mean, after this programming, but not very great performance.
Okay. So the next question is, what are the minimum hardware requirements to run and test ADA?
Well, I think there are no minimum. Well, I can't say that it can be run on smartphone. Well, probably it can, but I have never tried it. But overall, you just download and run it. So this, for example, this graphical user interface that I showed, you can download on any, well, Windows or I think Linux, Mac also. It can be run. And I mean, like the basic run, it will run always. I don't know. It requires like a few megabytes of RAM and something like that. But then you can always push it. So whatever computer you have, if you increase the particle size, it will stop at some moment, stops working. So, and the limits are, well, I would say that, for example, I have, I don't know, like 5 years laptop now, and I can get a grids, I think around 150 in one dimension. So its total number of voxels is like slightly several millions. So that can be done on laptop. But if you want to go to 1 billion, as I mentioned, then you definitely need, well, a huge supercomputer. And several million dipoles, that would mean usually a size parameter if the particle is not very complicated, so you don't need very fine details to describe, well, its shape or internal structure, then it will probably be, well, something like maybe 10 wavelengths or particle size. So already quite a lot, yeah, you can do on just laptop or whatever.
Okay, let me say, I don't see any more questions in Slido. So let me share our experience with ADA and the limits. So we have tried to simulate dust particles, the scattering of dust particles, and with a refractive index of 1.6 with the real part. And some absorption, two more options for absorption, and one smaller refractive index, real part of refractive index. But I guess the most difficult one was as I saw in your plot also, the 1.6 and non-absorbing particle. So we have succeeded in an HPC machine to simulate up to size parameter 60. 60. So, yeah. And then we cannot go any further. So still, we haven't checked this data for their accuracy. So we are now on the progress of comparing this data with other methods, with the physical optics approximations with Alexander Konovelski. So this is just to give an idea to the people that size parameter of 60, and we have used 50 million CPU core hours, so a lot.
Yeah.
A lot. So I agree with you that I think the way to go is to combine ADDA with a faster code for larger particles. And And this is now my question. What happens for backscatter? Because a lot of people here are from the LiDAR community. And I think the backscatter is challenging. And for example, with geometrical optics, we have a lot of assumptions there that maybe exclude the option of using geometrical optics for backscatter. So can you comment on the performance of or things we should pay attention to in when we have backscatter calculations with ADDA?
Yeah, that's a very important question, I think. So, well, the first important thing is that if you just take some papers that say, okay, we simulated like phase function and it's fine for this discretization, etc. So do not assume that it will be the same for backscattering. So it can be, well, maybe not always, but in many cases, to get good accuracy at backscattering, you will need finer dipoles. So in principle, as I mentioned, DDA is numerically exact method. So if you take fine enough discretization, then you will get good accuracy. But how fine it is, it's something that should be tested for a specific problem. Or at least if you use some guidelines from like published results, then you should be careful that you actually consider the results for backscattering, not for some other scattering quantities. So that's one thing. Another thing is also with respect to orientation averaging, because usually you have this orientation averaging, and that's also what I saw in publications that it also affects a lot. So how many orientations you use, and then that's also like if you compare the codes, for example, DDSCAT and ADA, the problem is that they have some built-in routines for this orientation averaging, but they are different. And then if you compare like two codes and you get different results, it can be both due, for example, different formulations of the DDA itself, or due to this different orientation averaging. For orientation averaging, if you use some clever scripting around the code, you can run the code like in fixed orientations and then do the averaging yourself. So that's also possible. But most users don't want to do it, so they just take the code. Okay, it has some built-in averaging, so you just use it. But then again, that's another thing to worry about. So because the codes, for example, ADA, it will try to use these adaptive routines, which try to use as many orientations as needed to get some converged results. But the problem is that in many cases, it will be too slow. So it will take, I don't know, like thousands of orientations or 10,000. And then, yeah, if you can afford so many simulations, then, I mean, it's fine. The only good thing about it that you mentioned, like in the beginning, this limit in terms of sizes. So the problem is how it happens that the number of iterations in the iterator solver, it increases with size. And first it goes quite slowly, but then more or less exponentially, so it becomes a prohibitive factor. So all the other factors, which is like when you refine discretization. For example, when you refine discretization, the scaling of computational time, it's more predictable. So if you take like twice smaller dipole sizes, it will mean you will have 8 times larger number of dipoles, and that will translate into, in most cases, about also 8 times larger computational time. So that's quite a lot, but still, sometimes you can afford that. So it's like when you reach the size of 60, that's already a problem. But if you go a little back to size of 50 or 40, and then it will give you some extra computational time, which you can use to actually tune the dipole size, tune orientation averaging, and have the good results. But overall, yeah, it raises like a lot of questions. For orientation averaging, there is a lot of motivation to use some optimal spherical quadratools or cubatools, which are called. There is a lot of research on that. There are some, ready-to-use methods, but they're not implemented in ADA or in DDSCAT, whatever. So you need to like run them themselves. But I think some people do it, and maybe they even have some, I don't know, Python scripts, which will basically interact with ADA to do this more efficient orientation averaging. So that's one way to go. For backscattering, for backscattering, the only thing you can tune in the DDA, I think, this formulation. And I think many people said that FCD formulation, well, which I mentioned, I mean, you don't need to understand what is it, just put in a command line option in add, which is written in the manual how it should be, and usually it improves the accuracy for backscattering. But still, you need just to try different options and see the results and ensure that it converges to the threshold of the error that you can tolerate.
And how do we define this error? Do we define it through comparing our results with other methods with all these problems you mentioned, or do we define it by, let's say, having a subset of more dipoles and see if you get different results, and then what would you recommend?
Yeah, so well, both. Yeah. So first, it's a good idea to consider some simple shapes, but the problem with simple shapes that usually when people say about simple shapes, they say, okay, it's spheres. So we compare with the Mie theory, and that's easy to do. But in many cases, well, you can get some conclusions like, okay, here is a sphere, you compute backscattering for this refractive index, and then you use so many dipoles, or so like that is the dipole size that you need to get, I don't know, 10% or 1% accuracy that you want. The problem is that you can't, this will not necessarily translate to other shapes. So in many cases, spheres are special, especially large spheres where you can have this whispering gallery modes or whatever. So that's more complicated. So in general, actually, again, like the good thing about DDA, that the more irregular particle, usually the less it's sensitive to like these shape errors, which you inevitably get into from the DDA because you describe the particle by a set of cubes smaller. Yeah, so this error decreases. So yeah, that's all can be well, even better. But that does not help you to answer the question. Okay, what is this error? So what we can do else is compare the DDA with itself, and that's what this shows. So this, well, the simple way, you just compute 2-3 different discretizations, and then you can assume like that the best discretization you use, the most fine one, will be like close to exact, and then you compare the other one with it. So that will give you some estimate of what is like the accuracy. If you want some more confidence in the results, then you can look at something like that as shown here. So basically you plot the results versus discretization and then do extrapolation. And then where it crosses at the vertical axis, so which corresponds to more or less infinite discretization. Then you can use this value as so this will be kind of estimate of the exact result. And because you do this extrapolation by some least square fitting, well, more or less, then you also get some error bar here. And that can be your estimate of your value. So that's like one of the options to go.
Okay. I should read a little bit more carefully this paper.
Yeah.
So is there any other question? I don't see any more questions here. Just a quick comment before we close the session, the webinar. From what I understand, because okay, we talked about dust, but from my understanding, DDA is very useful for ice particles and water droplets and So due to the small refractive index there, we don't have so much a big problem with the size parameter. So I guess this is a nice application.
Yes. So if we are talking about like visible wavelengths or like infrared, I think it will be 1.3 something. Yeah. So that's in many cases it will be, well, either better or comparable to time domain methods, for example. So overall, well, still you will go probably to size parameter around 100. Still, you will get the same problem as you have with 1.6 you had. So it's not kind of anything that you want, but still, yeah, you can extend it a little bit. But again, when we're talking about water, actually some of this application, they consider radar wavelengths, so microwave frequencies, and then it's very different. So ice, I think it's kind of moderate, but water becomes problematic.
Okay.
But it's also, it's not just that it's a large real part, it's also absorbing part. So that it's more what I called extreme in the conclusions. It's actually not necessarily that the iterative solver will break down, but it's more when you will worry about the accuracy. So the iterative solver will converge, not fast, but still converge. I don't know, maybe 1,000 iterations, something like that. But then probably you will need to use very fine dipoles. So not like 10 times smaller than wavelengths as we usually do. Well, usually it's 10 or 15 times smaller than wavelengths, but in some cases you need to go 20 or 30 dipoles per wavelength, especially if you're interested in backscattering. So I think there were some papers where they specifically studied accuracy of backscattering for these like water containing particles at microwave.
Okay. So Maxim, thank you very much. I was very happy to hear for this new option about the multiple refractive indices. That will be very useful.
Yeah.
That will be very, very useful. Thank you. I hope we have some interesting results soon and share it with you and proceed with this dust ADDA work.
Yeah, great. Okay, thank you for your invitation.
Goodbye.
Thank you, bye.
Thank you. Bye.
Thank you, bye all.
Thank you. Bye bye.